In the last class, we discussed the topic gain margin and phase margin. We will continue that topic. Gain margin and phase margin, and we considered the example having open loop transfer function equal to Kc exponential minus 0.123 s divided by 0.1 s plus 1. Fine. Now, when Kc equal to 2, we obtain marginal stability. This is the marginal stability condition. We developed in the last class the Bode plot like this. This is omega, this is phi, and this is a semi-log graph paper. Suppose this is the phi versus omega plot in semi-log graph paper. Now, crossover frequency we obtain considering phi equals minus 180 degree. So, this is crossover frequency. Now, above this we consider amplitude ratio versus omega, and this plot is produced in a log graph paper. Suppose this is the amplitude ratio versus omega plot when Kc equal to 1. So, at crossover frequency, the amplitude ratio we obtain, suppose that is m. Now, as mentioned, the marginal stability corresponds to Kc equal to 2. Suppose this is the amplitude ratio versus omega plot when Kc equal to 2. That means, at crossover frequency we obtain the amplitude ratio equal to 1. Fine. So, this is for Kc equals 1. So, we can say that we obtain stable response when Kc equal to 1, because at crossover frequency amplitude ratio is less than 1. So, we obtain stable response when Kc equal to 1, because amplitude ratio is less than 1 at crossover frequency. Now, this difference is called as gain margin. So, it is obvious that it is a safety factor. Now, how can we represent the gain margin mathematically? Gain margin we can represent as 1 divided by m. difference is log 1 minus log m. So, we can write gain margin as 1 divided by m, fine. Now, when amplitude ratio equals 1, suppose this is, I am just extending this like this. When amplitude ratio equals 1, how much is the corresponding phi? See, we are considering Kc 1. Previously also we considered Kc 1 and we obtained amplitude ratio m. Similarly, here we are considering Kc equals 1 and the corresponding value of phi is this quantity. Suppose this is phi prime, this one. So, when amplitude ratio equals 1, the corresponding phi we are indicating by phi prime, agree, and this phi prime is greater than, you see, minus 180 degree. Agree. So, we can say that we obtain stable response when Kc equals 1 because of the non-existence of crossover frequency. We obtain stable response when Kc equals 1 because of the non-existence of crossover frequency. See, this observation is based on this plot and the previous observation was based on this plot, and this difference is called phase margin, fine. This difference is called phase margin. You see, this phi prime is lower than minus 180, phi prime is higher than minus 180. So, similarly we can say that this phase margin is also a safety factor, and this phase margin is represented as (180) minus the absolute value of phi prime. The phase margin we can represent or we can calculate by this correlation, fine. So, these are two safety factors, and based on the values of gain margin and phase margin we can tune the control parameters. Now, next we will note down few points. So, gain margin is a measure of how far the closed loop process is from the brink of instability. Gain margin is a measure of how far the closed loop system is from the brink of instability. This is also true for phase margin, fine. So, they are the measure of how far the closed loop system is from the brink of instability. Now, the higher the gain margin, implies the higher the safety factor. The higher the gain margin implies the higher the safety factor. Now, question is how we can select the values of gain margin and phase margin. First, we will discuss the selection of gain margin, then we will discuss the selection of phase margin. The heuristics is that when the process parameter values are poorly known, first we have to know the process parameters. Process parameters means process gain, time constant, date time, etc. These are the process parameters. So, process gain is one parameter, then time constant, then date time, and so on. These are the process parameters. When these parameters are poorly known, imprecisely known, when these process parameters are poorly known, the gain margin is taken in between 1.7 to 3. This is the heuristics. When the process parameter values are poorly known, in that case the gain margin is taken in between 1.7 and 3. When they are well known, they are known quite accurately, in that case the gain margin is taken in between 1.4 and 1.7. These are the safety limits. Fine. And for phase margin, it is usually taken as greater than 30 degree. Phase margin is usually taken larger than 30 degree. So, these are the heuristics for selecting the gain margin and phase margin values. Next, you will solve one problem based on this phase margin and gain margin concept. In the next, we will solve one problem based on the phase margin and gain margin concept. The open loop transfer function is given as 0.8 kc exponential of minus 1.74 s divided by 5s plus 1, 10s plus 1, 15s plus 1. So, this is basically the transfer function of a third order plus date time system, and only P controller is employed for the system. So, this is the open loop transfer function of the example system. Now, we want to tune the controller, P only controller. Tune P only controller, taking gain margin equal to 1.7. Tune the P only controller, I mean find the Kc value considering gain margin equal to 1.7. Now, the open loop transfer function we can write as 1 divided by 5s plus 1 1 divided by 10s plus 1 1 divided by 15s plus 1. So, 3 first order systems connected in series. Next part is the date time part. Fine. We can rewrite the open loop transfer function in this form. Now, in the first step we need to calculate the crossover frequency. For finding the crossover frequency we need to write the expression for phi and we need to consider phi equals minus 180 degree. So, what will be the expression for phi? Tan inverse minus tau p omega is the expression for phi for first order system. So, for this first order system tan inverse minus 5 omega. For the second first order system tan inverse minus 10 omega, and for this first order system tan inverse minus 15 omega, and for the date time part minus 1.74 omega multiplied by 180 divided by pi, and we can write this is equal to minus 180 degree. Agree? We can write this is equal to minus 180 degree. See, when we write phi equals minus 180 degree, then that omega is crossover frequency. So, we can include the suffix CO, omega CO, here also omega CO, everywhere omega CO. Now, solving this we obtain the crossover frequency 0.16 radian per minute. Here time is in minute. Solving this equation we obtain crossover frequency 0.16 radian per minute. Now, we need to write in the next the expression for amplitude ratio. In the next we need to write the expression for amplitude ratio. So, for the first order system, I mean for this system, for this transfer function, what will be the amplitude ratio? 5 omega whole square plus 1. No, one thing we missed in this open loop transfer function, yeah, that is 0.8 Kc. We missed this numerator term 0.8 Kc. So, we can write here that term 0.8 Kc. For the next transfer function 10 omega whole square plus 1. For third one we can write 1 divided by 15 omega whole square plus 1. Fine. Now, we will substitute omega equals omega CO. Then we can write the expression for amplitude ratio as 0.8 Kc divided by 5 into 0.16 whole square plus 1, 10 multiplied by 0.16 whole square plus 1, 15 multiplied by 0.16 whole square plus 1, fine. This is equal to 0.8 Kc divided by the first term yields 1.28, next term gives 1.89 and third one gives 2.6, which is equal to 0.127 Kc, fine. So, at crossover frequency we obtain amplitude ratio this much. Suppose this is equal to m. Now, gain margin is given 1.7, this is given. In the problem, gain margin of 1.7 is given. Now, how much is gain margin? 1 by m, this is gain margin. That means, we can write 1 divided by 0.127 Kc equal to 1.7. Then how much is Kc? Kc becomes 4.62, fine. So, for the example system, if we consider Kc equal to 4.62, then amplitude ratio at crossover frequency is lower than 1, fine. So, this is the answer for the first part. Now, in this example, see, we calculated this Kc value considering the date time 1.74. Suppose that value is wrong, the actual date time value is suppose 2.42 minute, true value of date time is 2.42 minute instead of 1.74 minute. What about stability? If we use Kc equals 4.69, the question is what about stability? If we use Kc equals 4.62 when original Td is 2.42 minute, this is the second question. We found Kc value 4.62 based on the wrong date time value. Now, question is what about stability? If we use Kc equals 4.62 when the original date time is 2.42 minute. Now, in this situation, first we will found the crossover frequency considering this date time. So, again we need to write the phi expression, tan inverse minus phi omega c naught plus tan inverse minus 10 omega C naught plus tan inverse minus 15 omega C naught minus of 2.42 omega C naught multiplied by 180 divided by pi, and this is equal to minus 180 degree. Fine. In this phi expression we have changed only this Td value. Solving this we obtain crossover frequency 0.15 radian per minute. Solving this equation we obtain the crossover frequency as 0.15 radian per minute. Next we will calculate the gain margin. Our aim is to check the gain margin value. So, for that we need to determine the amplitude ratio. Amplitude ratio expression we know 0.8 Kc divided by root over of 5 omega C naught whole square plus 1, 10 omega C naught whole square plus 1, 15 omega CO square plus 1. Fine. 0.8 Kc we determined 4.62 and we are still using that 4.62 value divided by 5 multiplied by 0.15 square plus 1, 10 multiplied by 0.15 whole square plus 1. Next is 15 0.15 whole square plus 1, and we obtain this is equal to 0.666. This is the amplitude ratio value considering Td equals 2.42. Then how much is gain margin? 1 divided by amplitude ratio, I mean 1 divided by m, 0.666, and this is equal to 1.5. What about stability? This is stable because when m is less than 1, we say that the system is stable. So, gain margin is basically 1 by m. So, if 1 by m is greater than 1, then the system is stable. When m is less than 1, definitely gain margin should be greater than 1. So, this is the condition for stability. If gain margin is greater than 1, then we can say that the system is stable. So, the problem we have solved based on the gain margin value. We will continue this problem considering the phase margin of 26 degree. So, next question is tune the P only controller. When the phase margin is 26 degree. Find the Kc value when this phase margin is 26 degree. Now, we know the expression for phase margin. Phase margin we express as 180 minus phi prime. This is the expression for phase margin, 180 degree minus phi prime. 180 minus phi prime. So, what is the expression for phi? That we will write here, tan inverse phi omega, absolute term we are writing, I mean this is absolute value, no, plus tan inverse 10 omega plus tan inverse 15 omega plus 1.74 omega 180 divided by pi equal to 26. Fine. And this we have written based on this transfer function, GOL equals 0.8 Kc exponential minus 1.74 s divided by 5 s plus 1, 10 s plus 1, 15 s plus 1. Fine. We are solving this problem considering this open loop transfer function. I mean, using this open loop transfer function, you find the value of Kc when phase margin is taken as 26 degree. Now, if we solve this, then we obtain omega as 0.12 radian per minute. If we consider this part equal to 26 degree, and if we solve, then we obtain omega equals 0.12 radian per minute. Now, amplitude ratio equals 1. Basically, phi prime is the phi value at amplitude ratio equals 1. So, we will consider this here. Now, what is the expression for amplitude ratio? 0.8 Kc divided by root over of 5 omega whole square plus 1, 10 omega whole square plus 1, 15 omega whole square plus 1, and this is equal to 1. This is the expression for amplitude ratio, 0.8 Kc divided by 5 omega whole square plus 1 root over of 10 omega whole square plus 1 root over of 15 omega whole square plus 1, and that is equal to 1. Now, if we solve this, we obtain Kc equal to 4.69. Here only Kc is unknown. If we substitute omega equal to 0.12, fine. So, finally, we obtain Kc equal to 4.69. So, previously we obtained Kc equal to 4.62 considering gain margin 1.7. Now, here we are getting Kc equal to 4.69 considering phase margin 1.26 degree. Now, next question is the date time we have taken wrongly. So, the original date time is the true value of date time Td is suppose 6 minute instead of 1.74 minute. Now, question is what about stability? What about stability? If we use Kc equal to 4.69 when the actual date time is 6 minute, this is the question. What about the stability when we use Kc equal to 4.69 when the original date time is 6 minute? First we need to calculate phi prime. Expression is tan inverse minus 5 omega, tan inverse minus 10 omega, then tan inverse minus 15 omega, date time is minus 6. So, minus 6 omega 180 degree divided by pi. This is the expression for phi, and considering omega equals 0.12 radian per minute, we obtain this as 183.35. Substituting omega equals 0.12 radian per minute, we obtain the phi prime as minus 183.35. What about phase margin then? 180 degree minus absolute value of phi prime. So, 180 minus 183.35 minus 3.35 degree, which is less than 0. So, what about stability? Unstable. So, this is unstable problem, I mean unstable system. If the date time is 6 minute and if we use Kc equals 4.69, then the system becomes unstable. Fine. So, this is the problem related to this gain margin and phase margin. So, first we have constructed the Bode plot, then by the use of the Bode plot we discussed the Bode stability criteria, under which we determine the control parameter values. Similarly, we discussed the construction of Nyquist plot or polar plot. So, now we will use that plot for stability analysis. So, our next topic is Nyquist stability criteria. Nyquist stability criteria. So, we discussed a number of examples under this frequency response analysis, and we observed that with the increase of omega, both amplitude ratio and phi decrease. So far we have discussed the frequency response analysis taking a number of examples, and it is observed that with the increase of omega, both amplitude ratio and phi decrease. This is our observation, amplitude ratio and phi decrease monotonically with the increase of omega. If this is the situation, then it is recommended to use the Bode stability criteria. Then we can use the Bode stability criteria. Fine. If this is the situation, the Bode stability criteria leads to rigorous conclusion. If this is the situation, then Bode stability criteria leads to rigorous conclusions. But there are few systems for which amplitude ratio and phi do not decrease. Continuously with the increase of omega. There are very few systems in chemical engineering for which the amplitude ratio and phi do not decrease monotonically with the increase of omega. And the plot looks somewhat like this. This is suppose amplitude ratio versus omega plot in log graph paper. Here suppose the value is 1. So, it goes like this. Similarly, the phi versus omega plot, not the corresponding plot, I want to say for few systems the phi versus omega plot is somewhat like this. Fine. So, it is very clear that the amplitude ratio and phi do not decrease monotonically with the increase of omega, and in this situation it is not recommended to use Bode stability criteria. If this is the situation, then it is recommended not to use Bode stability criteria, and it is recommended to use Nyquist stability criteria, which to be discussed in the next. In this situation, the Bode criteria leads to erroneous conclusions. In this condition, the Bode criteria leads to erroneous conclusions, and it is recommended to use the Nyquist stability criteria. This criteria was proposed by Nyquist in 1932 and which has been published in a journal, namely Bell Systems Technical Journal. The Nyquist stability criteria was proposed in 1932. The title of the work was Regeneration Theory. And this work was published in the journal, namely Bell System Technical Journal. No proof of the theorem will be discussed in this course, and you are strongly recommended to go through this paper if you are interested to know more about the Nyquist stability criteria. So, what is that criteria? Nyquist stability criteria we can write as a closed loop control system is unstable a closed loop control system is unstable if the open loop Nyquist plot of the feedback system encircles the point -1 0 as the frequency omega takes any value in between -infinity and infinity. A closed loop control system is unstable if the open loop Nyquist plot of the feedback system encircles the point -1 0 as the frequency omega takes any value in between -infinity and infinity. So, previously we construct the polar plot in the complex plane. So, this is the complex plane. First we draw one unit circle, fine. This is a unit circle. So, this point represents, suppose this O is the origin, this is point A and this is point B. A is basically 1 0 and B is -1 0. fine. Now, if the Nyquist plot do not encircle this, then the system is said to be stable. It is somewhat like this. Suppose for a particular system we are getting, say for a third order system, we are getting this polar plot, and this plot we obtain varying, suppose omega 2 from 0 to infinity. Another plot we are getting, suppose this one. So, this plot we can obtain varying omega minus infinity to 0, and this we obtain varying omega from 0 to infinity. Now, you see this Nyquist plot do not encircle this minus 1 0 point. So, we can say that the example system is stable. So, in the next day we will discuss this Nyquist plot with taking one example. Thank you.